On this presentation, we are going to talk about the various types of damping system exist in vibration engineering. Here, we can distinguish what does the damper do on a mechanism or its application on machines and buildings. First, what is damping? So damping is a decrease in the amplitude of an oscillation as a result of energy being drained from the system to overcome frictional or other resistive forces. Damping is an influence within or upon an oscillatory system that has the effect of reducing or preventing its oscillation. In physical system, damping is produced by the process that dissipate the energy stored in the oscillation. Damping ratio is a dimensionless measure describing how oscillation in a system decay after a disturbance, or a parameter, usually denoted by the Greek letter zeta, that characterizes the frequency response of a second-order differential equation. This measures how much damping exists in an oscillating system. So damping ratio denotes that when undamped means no damping in the system, also tells the system will keep oscillating. An underdamped system will oscillate through the equilibrium position, while critical damping returns the system to equilibrium as fast as possible without overshooting, and an overdamped system moves more slowly toward equilibrium than one that is critically damped. So for the types of damping, the first one is viscous damping. Damping that is proportional to the velocity of the system. The faster the mass is moving, the more damping force is resisting that motion. Examples of fluids like air or water generate viscous drag forces. Oil is the most common substances used for a viscous damping. The commonly used fluids for dampers are synthetic oil or mineral oil. Damping of the oscillation amplitude increases when the increase of the frequency and is inversely proportional to the viscosity of the fluid. In contrast, the penetration depth decreases with the increasing frequency and is directly proportional to the viscosity of the fluid. Next one is hysteric damping. It is due to slipping between microsurfaces. Heat is generated and energy dispersed. Different from viscous mechanism, magnitude of energy loss depends upon material type and mode of vibration. In hysteresis damping, some of the energy involved in the repetitive internal deformation and restoration to original shape is dissipated in the form of random vibrations of the crystal lattice in solids and some random kinetic energy of the molecules. There are common damping systems that exist in machines and in structural design. First is free layer damping or constrained damping. For free layer damping to be effective, the damping material should be between 1 or 2 to 3 thickness of the surface being damped. Means the ratio must be 1 to 3 times. This type of damping is commonly used to reduce structure-borne noise, noise that occurs from an object hitting a surface, such as the floor, ceiling, or wall. Free layer damping is more effective on large, thin vibrating surfaces, such as metal chutes, hoppers, and machine guards. Second is constrained layer damping, which involves sandwiching the damping material, such as synthetic rubber, between the noisy equipment and a layer of steel or aluminum, which helps to transfer energy into the damping layer. Also, constrained layer is commonly used to minimize unwanted vibration. This is a technique for suppression of vibration. Typically, a viscoelastic or other damping material is sandwiched between two sheets of stiff materials that lack sufficient damping by themselves. The third one is the June damping. Its oscillation frequency is tuned to be similar to the resonant frequency of the object it is mounted to and reduces the object's maximum amplitude while weighing much less than it. So example of this tune damping is the famous Taipei 101 skyscraper. So inside the skyscraper is the largest and most heaviest tuned mass damper, essentially acting as a giant pendulum. The enormous steel sphere moves slightly back and forth to the counter any motion of the building itself. So other type of vibration control, which is the process of isolating an object, such as a piece of equipment from the source of vibration. Vibration is undesirable in many domains, primarily engineered systems and habitable spaces, and methods have been developed to prevent the transfer of vibration to such systems. Vibrations propagate via mechanical waves, and certain mechanical linkages conduct vibration more efficiently than others. The difference between the two is that vibration isolation prevents vibration transmission. It keeps vibration energy from entering an object such as structure or piece of equipment, while vibration damping dissipates vibration energy. It absorbs or changes vibration energy or reducing the amount of energy transmitted through the equipment or structure. So isolator tends to eradicate all signs of noise or vibration in a system, while damping minimizes the impact of an oscillation of a system. And still, both are capable of controlling resonance at different levels.